everybody. Um, I'm going to be out for a few days. My dad had a heart attack, so I'm going back to Michigan. And so that's why I'm not in school. Um, he's doing okay, so it's not like really, really bad. Don't freak out. But just wanted to let you know I'm also recording this in a vehicle somewhere in Wisconsin. So if you hear background noise, that is why. You also might hear the football game in the background because Gabe is listening to the football game. So, basically, we're going to do recorded notes. So, I'm going to go through the slides and kind of talk you through it. And you guys are going to be pausing the video and writing down information that is on the slides. Okay? So, I just want you to do your best going through this, and I'm going to try and simplify it. Uh, understand that this subject could be a lot more complex, but because I'm not there, I'm just going to focus on some basic things with you guys. And so I'm going to also upload some video resources to help you guys. And some of the video resources might go into a little bit more depth or a little bit more on bond angles or even more molecular geometry shapes. But what I'm focusing on in this slide is all the stuff that you'll be tested on in our test. So just focus on this PowerPoint. And then if you want to use extra resources to help you, you're welcome to. But those extra resources will probably go into more depth than I'm going to require from you guys. So, all right. So let's get going on our notes. This is over molecular geometries and bonding theories. Okay, so we focused on Lewis structures up until now. Also, I'm sorry if my voice just cuts out. It was a long weekend of a lot of screaming at volleyball games. So, anyways, so we've talked about Lewis structures, and you guys have modeled Lewis structures, and you have drawn them, and I'm very confident that you are good with understanding Lewis structures for compounds. So, molecular shapes. Basically, molecular shapes use Lewis structures and they give us a more real representation of what the atoms are, how the atoms are bonding, okay? Lewis structures are really basic and that's great, but when we want to be in a little more depth of understanding, we want to use molecular geometry. Sometimes it's also called VSEPR. So Lewis structures really limit us to a 2D view, and molecular shapes are really 3D. So by understanding the shapes, we kind of understand a little bit more about the three-dimensional view of the electrons and the interactions of the different atoms. Okay, so molecular shapes. Geometry and shape of a molecule they're going to be critical when we talk about bonding. Okay, and we can easily predict the 3D structure of the molecule just by adding up the bound atoms and the lone pairs. And we'll talk about each one of those in the future, but really the way we get molecular shapes is by understanding the repulsion between bonded electrons and lone pairs of electrons. Okay, so what determines the shape of a molecule? Atoms and lone pairs take up space and prefer to be as far away from each other as possible. Okay, we know electrons have negative charges, and we do know that they're both paired up. And the reason they're paired is because they have a different spin. So one will spin clockwise, the other will spin counterclockwise. And by spinning differently, they can actually pair up. But really, the pairs want to be as far away from other pairs as possible. Okay, and shapes can be predicted by just using some simple geometry and by using the understanding that electron pairs want to be as far away from the other electron pairs as possible. Okay, so if you haven't looked at this NH3 molecule, it's just the Lewis structure of the NH3. And you know already that there's a bond between each of the hydrogens and the nitrogen, and then there's a lone pair of electrons on the outside of that nitrogen. Okay, so each bond and each lone pair, they're going to repel each other a little bit differently. Some are going to be a little stronger and some are going to be a little weaker. And we'll learn about that. And that creates the geometry. Okay, so we're going to talk about things. Okay, and these things are things around the central atom. And the central atom is just exactly how it sounds. It's the atom that's in the center of the shape. Okay, and a thing around it is either a bonded atom, it could be a single, double, triple bond, but an atom that's bonded to it, or a lone pair of electrons. Okay, and the number of things equals the lone pairs of electrons and the atoms that are bonded. Okay, so if I'm looking at this example molecule, this road is really bumpy, I'm sorry. So if I'm looking at this example molecule, A is our central atom. Okay, so it's element A, which is not a real element. But you can see the element A is bonded to element B. And it's bonded to three element B's. Okay, so atom A is bonded to B with a single bond, and then atom A is bonded to the other B with a double bond. Wisconsin has horrible roads. I keep laughing. I'm sorry. I'm not redoing this video for you guys. Anyways, element A is bonded to element B through a single bond, and then a double bond, and then another single bond. Okay? So even if it's a double bond, we're just going to still call it one thing. Okay? And I know thing is not very scientific, but I've really found that focusing on just the things that are around the central atom helps with electron geometry. Okay? So we have three bonds. Okay? A bond here, a bond here, and a bond here. So there's three things, and then we have a lone pair of electrons here. So that's going to be four things around this central atom. Okay, and the number of things is going to help us understand the electron geometry. All right, so VSEPR is just the valence shell electron pair repulsion theory. And it just states that the best arrangement of a given number of things is the one that minimizes the repulsion among them. Okay, so pretty much you're going to want to make sure that everything is spread out evenly, and so that repulsion is balanced. Okay, so geometries. So these are all of the geometries for 2 through 6 things around the central atom. Okay, so we're going to learn all of these 5 electron geometries. All right, there's more. There's more in depth than this, but this is what we're focusing on. Okay, so we're going to go through each one of these a little bit more in depth, but this is kind of an overview. And you can see on the left, we have the number of things. So those are our bonded atoms or our lone pairs of electrons, or I guess our pairs of electrons. And then you have an arrangement here. This is kind of what it looks like. And then we have geometry and bond angles. Okay, so geometries. What we're going to do is we're going to start with the Lewis structure, and then it's going to create this geometry, this bond geometry. Okay, so all you have to do to figure out the geometry and the shape of the compound or the molecule is count the number of things. Remember, the number of things is paired electrons and then bonds. And the geometry will be that which corresponds to the number of things, okay? So if you have 3 things, you're gonna have a certain geometry. If you have 4 things, you're gonna have a certain geometry. And we'll talk about each one of those. So the geometry is often not the shape of the molecule, but it's really the shape that's defined by the positions of only the atoms in the molecules, not the lone pairs, okay? So we're focusing a little bit more on the type of atoms that are in it and a little bit less about the electrons around it. Okay, so then once we understand the geometries, each geometry can be broken up into a specific shape. Okay, so within each geometry, there might be more than one shape. And here's some examples: tetrahedral, trigonal, pyramidal, and bent. Those are all shapes that are within, that can be within geometries. And we'll talk about each one of those. Okay, so in a linear geometry, that means that there are going to be 2 things, okay? So it could be 2 bonds or 2 areas of lone pair of electrons. Okay, and in this geometry, there's only one molecular geometry. It's just linear, okay? So if there are only 2 atoms in a molecule, the molecule is going to be linear, okay? So it doesn't matter what the geometry is. When there's only 2 atoms, it's always going to be linear, okay? So I want you to write down linear. I want you to write how many things there are, how many lone pairs, the shape, and give an example. Okay, so jot down everything on this slide. And I think my AirPods are going to die, so let's go. Trigonal planar geometry, okay? So when something has 3 things around it, it's going to be a trigonal planar geometry. And then just dividing the geometry up, you can have 2 different shapes of the trigonal planar geometry. So you can have just a regular old trigonal planar, and that occurs when you have 3 bonds. All right, so trigonal planar is going to occur when there's 3 bonds. Okay, so jot down that, and there's the example. So that'll occur when there's 3 atoms around it with 0 lone pairs. If there are 2 atoms around the central atom and 1 lone pair, that's going to create still a trigonal planar geometry, but the shape is going to be called what we call bent. So here's that, and there's an example. NO2 is an example of a bent trigonal planar. Okay. Now, lone pairs and bond angles, okay? So lone pairs are physically larger than atoms. Okay, so they're going to take up more of a space. And because they take up more space, their repulsion is going to be greater. And this tends to decrease the bond angles in a molecule. Okay, so if you have lone pairs of electrons, what it's going to do, it's going to squish those bonded atoms a little bit closer together and further from the lone pair of electrons. And that's just because the lone pairs, they take up more space. So you can see in these bottom molecules, if I have a bond with 4 hydrogens and 1 carbon, the bond angle is 109.5 degrees. But then if I have a bond angle between, if I have a bond between nitrogen and 3 hydrogens, there's going to be a lone pair of electrons on that nitrogen. And therefore, those lone pairs are going to squish the 3 hydrogens a little bit closer together. So that bond angle is only 107. Okay, and then if you have 2 lone pairs of electrons, like my third molecule here, it's going to squish those bonded atoms even closer together because those lone pair of electrons take up more space. Okay, so if we have multiple bonds and bond angles, so double and triple bonds place a greater electron density on one side of the central atom than a single bond. Okay, so if you have double and triple bonds, they can also affect the bond angles. And you can see that in my molecule, okay? I don't make you memorize those specific bond angles. Just understanding how different bonds and what is bonded can change that geometry slightly as far as the angles that are between the atoms. All right, so now tetrahedral geometry. If you have four things, you're going to have a tetrahedral geometry. Okay, so jot down this whole chart. The number of things is four. The geometry is going to be tetrahedral. So if you have four atoms around the central atom, you're going to have just a tetrahedral shape. The geometry and the shape is going to be the same, tetrahedral. Okay, easy. If you have a geometry, it's still going to be a tetrahedral geometry, but if you have three atoms around it and one lone pair, you're going to have a trigonal bipyramidal shape. Still a tetrahedral geometry, but the shape is going to be trigonal pyramidal. And then if you have two atoms and two lone pairs, you're going to have a shape that is called a bent tetrahedral. Okay, so make sure you're jotting this one down, write those examples, add them into your notes. Okay, so trigonal bipyramidal geometry is going to be five things. And really, you just can write this title down and jot down an example here, okay? That's what's important. When you have five things around it, it's going to be a trigonal bipyramidal geometry, okay? We're going to skip through this because this is a little bit too in-depth for me not being there right now. All right, so jot down these. These are all the different shapes that you can have in a trigonal bipyramidal. We already know that trigonal bipyramidal has five things around it. So if you just have five atoms, just a regular old trigonal bipyramidal. If you have four atoms, one lone pair, it's going to be called a seesaw shape. If you have three atoms, two lone pairs, it's going to be called a T shape. And then if you have two atoms and three lone pairs, it's going to be called a linear shape. So you can have a linear trigonal bipyramidal. It's kind of weird. Make sure you've got all of these ones down. Okay, octahedral. Octahedral geometry has six things. So if you have six atoms and zero lone pairs, it's just a regular old octahedral. If you have five atoms and one lone pair, it's going to be a square pyramidal. If you have four atoms and two lone pairs, it's going to be a square planar. And it keeps going, but for us, we're just focusing on three of these shapes that are possible with our octahedral geometry. In larger molecules, and you go into this more in organic chem, we don't get into that much, but with larger molecules, what oftentimes scientists do is they focus on the geometry around one atom, okay? So not the whole geometry of everything. So they're gonna look at the carbon and they're gonna say, okay, carbon has four bonds, carbon's gonna be a tetrahedral, okay? And then they're gonna look at the other carbon and they're gonna say, okay, that carbon has three bonds. So it's going to be a trigonal planar, okay? And then it continues to go on, so forth and so forth, onward and so forth. So this is more applicable, and you've probably focused on this in advanced bio, but for larger molecules, the structure of the whole molecule is only clear when we look at the whole molecule, okay? So we have to look at the whole molecule to really understand the structure, but the geometry about each atom still is going to follow those same rules with the amount of things that are around that central atom, okay? Really, you don't have to write this slide, okay? Polarity, we're going to talk about polarity a little bit later, but really, it focuses on the electronegativity of each atom in the bonds, and understanding that electronegativity is the ability for an atom to pull electrons. So different molecules are going to have, different atoms are going to have different electronegativities. So they're going to have more or less pulling power. And that pulling power actually changes some of the bond angles sometimes, and it creates a dipole moment, which we'll talk about, but not today. Maybe not this week. I'd like to be there to talk about this stuff more. So, yeah, that is all that we need to talk about for now. Okay, so you can stop your notes. Make sure you go back and you have everything written down. I'm giving you a lot of time on these notes because there are tough tables to write down. Some of these drawings are a little complex, but I really want you to have good notes, okay? So it's all self-paced. Get through it. Um, have this as reference as you go forward. And I ask you, okay, draw this Lewis structure. Now tell me what the geometry will be. Tell me what the shape will be, okay? And you guys have a worksheet that's going to be on Google Classroom. And you should be able to type right in the worksheet. I'm going to try and do it that way. So you don't have to just copy down the worksheet because I can't be there to print it off for you guys. So you should all have access to a doc, and then you can type your answers right in the doc. If you're like, I hate doing that, you're welcome to jot down the number on a scrap sheet of paper and then put the answer and turn it into the bin. But that's kind of where I'm at right now, working virtually from Michigan so I can be with my family and help support my dad who needs a little extra help right now. So I really appreciate you guys understanding. Please be good for the subs. Please do your work so we're not way behind. And let me know if you have any questions. Other than that, I do apologize for the quality of this video, but I've been in the car for 17 hours, so I'm not that sad about the quality. Sorry, guys. A little bit, sorry. Okay. Have a great day.